Good morning and welcome to my talk on optimizing graphics for mobile devices ENT. My name is Brian and I'm part of the Not Doppler team. So I went a bit slide crazy today, so we might play a little game called do 100 slides in 50 minutes. But they're pretty short each, but I might ramble, so maybe someone should just throw something at me. So today's focus will be on our game Crash of Cars. It was our first in-house game, and it's had more than 25 million downloads, I'm pretty sure, around there. So I think it's a pretty good case study because it's been on so many different devices. So before we start, I'm just going to play a short trailer. Everyone likes that. Wake you up a bit. So hopefully there's audio. I don't know. It might be a silent trailer. I think it is. So maybe I'll talk over it since there's no audio. So it's a multiplayer car battle game. We worked on it for about a year. Pretty small team. It only started off with one artist and one programmer. Now I think we have 5 programmers on now. So if you have time, please download it on Android or iOS and just give us your opinion and feedback. You'll probably see some guys walking around with the Crash of Cars t-shirts, so talk with them, please. So quickly about me, I'm from the States, if you can probably tell by my accent. But now I live in Sydney, and I've been programming for about 10 years on a bunch of different platforms, and I was the first person on the Crash of Cars team since its inception, and kind of like a self-taught graphics programmer. So enough about me. So what are we going to cover today? So we aren't going to cover really script-based things like garbage collection or analyzing spikes and profilers. I'm just going to kind of focus on more like GPU-related stuff like reducing vertex count and fill rate. So those are kind of your true enemies on mobile devices. So, yep, let's get into it. Here's the obligatory contents, which I'll just read directly. Efficient terrain shading, how we shaded the game's levels, how we did shadows, and something called immediate drawing, which is a technique we use for 2 things called blob shadows and reducing some GUI overdraw and vertices. And another quick UI, reducing UI fill rate. Bit on car shaders and profiling in Xcode. There's one more section where it's a bunch of experiments I did. If we have time, we'll go into that, but I don't know if people have questions, I might just skip over. Okay, that was supposed to transition in first, but let's go on. First keynote presentation. So the terrain shader is very, very minimal, right? It's a CG shader, and it's not a surface shader. And lighting, as you know, is mostly done in vertex shader. We only support one directional light plus a shadow map. And only for types of terrain textures, types as I mean like grass, rock, sand, and stuff. So this is pretty much how all terrain shaders work, basic ones. So we just cut everything down to a bare minimum. So just if you don't know exactly how it works, this is kind of the breakdown. We have a splat map. Splat map basically tells where a texture goes depending on what color it is. Like red is grass, green is rocks, and alpha channel is kind of bricks. Then we have a shadow map. So this is a bit different from a light map. So some of you might think, oh, we just make a light map, but it's actually, the shadow map isn't UV mapped. It's actually projected down onto the terrain. So it's a little bit different from a light map. So we combine those two and we get that kind of result right there. Yeah, so kind of going into UV mapping, I think UV mapping is probably the trickiest thing to do on terrains. So often what people use is something called triplanar shading. So triplanar shading is basically kind of box mapping if you're an artist. So you're taking one texture and sampling it 3 times for each plane, the XZ, YX, and YZ plane. Then you combine all those 3 samples by the normal of the surface. So you can see on a sphere right there, all those colors represent one plane like that. So it's a really good technique, maybe on the console or PC, but it requires 3 texture samples for every kind of unique texture. So I think that was a bit too much for our game, because we have 4 different types of terrain textures. And if we did triplanar shading, that would be 12. And that's excluding things like the splat map and the shadow map. So you're doing 14 texture samples, which I'm assuming is not good. And also, we'll also get into a bit later, but it's not only the complexity of a shader, but how much it covers the screen. So we kind of thought our game's primarily a 2.5D game, in the sense that it is 3D, but height isn't that important in our game. So the most, I guess, dominant plane or the important texture plane is the XZ plane, right? So we just took a single plane. It's a nice GIF animation. And so we're just taking one texture sample. We're just taking the XZ plane. But of course, this has a bit of a disadvantage, because what's going to happen is you're going to have stretching on kind of the y-axis or any kind of steep slopes or walls. So we did the simplest thing. We just covered it up with geometry like that. So I don't know if you can see exactly, but you can see kind of the stretching right there. It might not be that visible on there, but it works quite well, right? It's a limitation, but you have to understand that you have good artists. We have very good artists, and you have to leverage that, because often they'll come up with creative ideas. So give them less at the start, then they don't actually know you can actually do more for them, and just let them handle it for a while, and you'll see what they come up with, basically. And this is the result. This is quite pretty. And you can see primarily the main part of the map is just using that terrain shader, and you can see the walls. It's just using different types of geometry right there. So that was just a quick blurb of how we did the terrain shader. So now I'll go into a bit of the shadows. Okay, there you go. So shadow types are, we have 3 types of shadow types. And so the first one is dynamic objects, and this uses Unity's built-in shaders. So if you want to sample shadows from Unity, you use a macro called light attenuation, and you do a bit of setup in the vertex shader, and that'll give you back a shadow. Then we have static objects, which was basically that shadow map we baked in to Blender. So this is just a quick way to optimize things, bake static stuff into the shadow map. Then the only thing you need to render is the dynamic shadows. And the third type, I'll talk to you a bit later. So if you want them to blend seamlessly, all you have to do really is multiply. So if you multiply those 2 values together, they'll blend like that. So it's really hard to tell. You can tell the baked shadow maps, of course, are a bit softer. The real-time shadow maps, they're more crisp like that, but most people won't notice, like the standard mobile game player. No offense to anyone, sorry. And so we also do a smooth step. So smooth step is, I think it's a Hermite curve or some kind of curve, and you use that with a little blend factor. You can actually control a slider to make the baked shadows a bit sharper or smoother. So if you want to kind of make everything sharp, you can use the smooth step function, or make it a bit blurry. You can use a lower factor like that. This is just a nice trick. So now here comes a bit of what we did with a trick we did with the baked shadows. So I mentioned before, the shadows are kind of a top-down projection, and they're not actually UV mapped. So the terrain has no UV data. And inside of our shadow map, it only contains shadow, unlike a light map, which might contain like lighting and bounce light and stuff. So we can actually reuse this kind of for dynamic objects. So all we have to do for any dynamic object, we just get the world space position of it, the XZ coordinates of it, and we just sample that same shadow map. So at first we thought, oh, this isn't going to work. It will look like junk, but you see it looks pretty well. It works pretty well like that. And just if you don't understand it exactly, I'll show you an example right here, why I call it 2.5D shadows. So you see the limo cast shadows, get shadow, receive shadows. But when we lift it up, it doesn't actually come out of the shadow because it's just a top-down projected shadow. But most people don't actually know this. And another thing we do is, well, we don't actually use it much, but we have a green channel that can mask out that kind of shadow. So this is a combined result. So if you're just playing the game, you won't really notice those kind of artifacts because we have smoothly blended shadows and the hot dog car, my favorite car, receiving shadows like that. So the fast way to do kind of bake shadows and receive, and also having hot dog cars receive shadows. Yeah. So another trick, I guess for artists, is just low shadow, poly shadow proxies right here. So you can see the car itself doesn't cast any shadows, but we use a low polygon model to actually be the shadow caster. And Unity has made this really easy because you can just toggle on shadows only. Yeah, that's about it. Just tell your artists to do that. I'm sure they like making that stuff like LODs. So basically, I always just bake what you can, both into light map. And if you can bake some kind of representation of not only the light map, but the shadow data, then you can optimize performance a lot. So even if your game is not 2D, you can also do 3D shadow maps by baking and storing the shadow map that the light casts. I might go into it a bit later, but it's kind of the similar method. And if you use kind of a top-down game, just give that a go and see if that projected shadow actually works for you. Yep. Then something called immediate drawing. I changed this title like 3 times, but I think this is the best one. So one of the things, like when you render to a render texture, is you often use like a camera and drag a render texture to it. But there's actually a different way to render to a render texture not using a camera or not using graphics.blit, and also not waiting for the render loop. So I just kind of call this immediate drawing. So there are 2 functions you can use in Unity that draw immediately. One is the GL class and the graphics draw mesh now. So if you're an OpenGL programmer, GL might be familiar to you. It's just basically a way to draw, vertices and UVs directly by defining points and UV coordinates and kind of setting render states. So it's like a low-level, well, what it says right there, low-level graphics library. And when you render using GL, it renders immediately. You don't have to wait for Unity to go into its render loop and wait for it to render everything and batch everything. Same with graphics draw mesh now. So if you use graphics draw mesh, then graphics draw mesh is a bit similar, but it renders immediately. So what you can do basically to render into a texture, all you have to do is you just set your render target to the render texture, clear it, and push your matrix. Pushing your matrix basically means saving your old projection matrix. Then you load a matrix. In this case, I use load ortho, so I'm loading an orthographic matrix. But you can load a perspective matrix, and they have a special matrix called pixel matrix, which is kind of a nice way for a one-to-one relationship for a unit to 1 pixel. Then inside there, you draw all your GL commands or your graphics draw mesh, and voila, you have a way to draw to a render texture without using cameras and without using game objects. So that's why I like this a lot. So whenever you use a camera, there's always a bit of overhead. Things like culling, and I think Unity also determines what lights are affecting certain meshes. So I think this is really good, efficient. It's also a compact way to draw these kind of textures. So it's not used primarily for rendering meshes, but think of it as a way, as I usually say, like a ghetto procedural texture. Yeah. So what can you kind of do with this? So here's one example. You can render a sine curve. So exact same code before, but just what's in the middle. So for every single point on the sine curve, I just draw 4 vertices using GL vertex. And just loop through how many I want, and it draws that sine curve right there. So that's like one kind of procedural texture. And so here are some more examples, like the sine curve. Then I also drew a star field like that. And it's quite efficient because if you think about it, you're taking out everything like transform.position and all the game object overhead. So this right here, I actually rendered 16,000 little pixel stars at a frame rate of 147 frames just using that immediate drawing. So it's a fun thing you can test out and do a lot of cool things with. So now I'm going to go over a few of the use cases for it. One is blob shadows in our game. So this is a third type of blob, not the third type of shadow we use. Sorry. So why not use a projector? Well, if you use a projector, everything that it projects on renders twice. So let's say you have a little cube with a blob shadow projector, then it hovers over a terrain piece, then suddenly you're rendering that entire terrain piece twice. So I think you have to be really careful with projectors when you use them, especially what meshes they go over. Why not use a shadow quad? Well, that works, but they never kind of perfectly align to the terrain. And you often have to do things like physics raycast to find the normal and line the mesh. So what we did basically is we just created another render texture, and this maps to the terrain similarly, or exactly same as what the projected shadow map does. Then for each dynamic object, we just pass in the position and we render GL quads to it. So here's a little breakdown. So that's the shadow map, the baked one. Then we create another render texture, and for each dynamic object, we just do GL quads. So technically, we can render a heap of things like 5,000 different little blob shadows all over, and I think the performance overhead wouldn't be that bad, yeah. Then what we do, we just blend it back with the baked shadow map. Then voila, we have hot dog car with blob shadow. So you can see on the bottom right there. So we do this for lower end GPUs because we don't want to render native Unity shadows. And once again, no camera needed, no game objects. So if you have more game objects coming in, you don't have to create new game objects, save a list of them, all that pain. So now I'm going to talk to you a bit about caching GUI text. So there are cases, like usually what we do is we use TextMesh Pro, but we can't always use it in that case. So in our game, we have little score indicator, so you can put your username right above it. And the issue is that, so we support 14 languages. Everyone plays our game all over the world, right? So usually we want to use a nice plugin like TextMesh Pro because that gives you nice outlines using signed distance fields. But we can't always, because what the requirement of TextMesh Pro is that you have to pre-generate a font atlas before you actually use it. So you have to know every single character that's used in your game before you can actually use TextMesh Pro. So that's a problem. So sometimes you have to resort to using like plain old Unity text because it supports dynamic fonts. Yeah. So fonts don't look too good on UGUI compared to TextMesh Pro. So for example, let's just get some lorem ipsum right here, and let's put it down, and you can see it's not too bad, 468 tries and 936 verts. So what's one common effect is just like the outline or the shadow, right? So what do you think will happen if we just add an outline and a shadow? So we're at 468 tries, and well, let's say 500 tries and 1,000 verts. Bam, 4.6. K, then we jumped up to 13.9 K verts. So it's a huge jump just for adding those outlines. So if you can go back, yeah. So imagine if you added another outline effect over there, then you'd be just rendering something like 30,000 verts for that paragraph of lorem ipsum, which you do not want to do. So the reason why is what GUI does is just basically renders the text 4 times for each outline, which is, I don't know why I do that, but like that's how it is. So it's not only a vertex issue, it's also a fill rate issue because you're rendering that text which is a transparent quad, 4 or 5 times. So what's the easiest solution? Okay, so usernames don't change in the middle of a game. No one's going to stop playing the game. We don't want the player to put in their name while they're driving and stuff. So we can just draw it directly to a texture. So, and can we use the same method we did before using that immediate drawing? So in order to do that, we need the UVs and the vertices. So how do we get UVs and vertices from Unity text? So there's a magical class called text generator. I didn't know about this, and made me very happy when I found it. So it basically does what I want it to do. So what you can do here in the code, this is some sample code. I'm not sure if it will compile, so don't try to do it. You can grab some source text, like that's a standard GUI text, and you can get something called generation settings. So this is all kind of styling of the font. Then you create a new text generator object, and you call populate with whatever text you want along with those settings. Then what will happen next is you can pass in a list of something called UI vertex, and you pass that into text generator, get vertices, and this will return all the vertices, all the UVs, everything you need to render the text. So now you have a way to get vertices and UVs to render text. So we have those, then we can just draw it directly again. So that's the code right there, but all we're doing is just taking all that data from UI vertex and rendering it into a texture. So now we have a nice way to render text directly into a texture and cache it. And that made me very happy, yeah. So that's the result. Now it's only one single transparent quad. So what we also did when we baked it, we just render it 8 times around the center to generate a nice outline like that. And another bonus of that is we get to do any kind of texture-based and shader effects to it. Yeah, so it's pretty good, and we also optimized it by just creating a pool of render textures. So we just have one function that says render text to texture, and it returns back one of those render textures to the pool. So I think it's a pretty cool trick. So if your game is very text heavy, and maybe it's like an RPG game and you have stats on the side and stuff, you can still probably use it because you will probably only need to update those stats like every 10 seconds or something like that. So here's another quick fill rate trick we did. So when you look at games kind of like Clash of Clans and Candy Crush, like they have a lot of these pop-ups here, and they're basically just a pop-up that's a rounded box and stuff. So you can kind of break them into different sections. Like you have the outline, which is always transparent, and you have the middle, which is an opaque fill. You combine those together and you get your rounded box. I know there are more different variations, but I think a lot of games just use that. So what you can do as a quick trick is just get the built-in shaders from Unity, pop them open, take out Z-Write, and take out blending. So your middle part now writes to the Z buffer. Sorry, Z buffer. And so anything that renders behind it will be discarded because it's writing to the Z buffer. So I did a test on iPhone 5S, 10 full screen pop-ups, and we can see it went from 3.35 milliseconds down to 0.9 milliseconds. So I think the results will be actually a lot better on things like iPad 3. So don't be afraid to modify UI default shaders because you don't know what Unity is sticking in there. Because Unity usually gives you everything inside of the shader and often features you don't need. I think it's a lot better now because in the older versions of Unity, I think masking operations used to be applied to every single shader, even though you weren't using a mask. So if you are using an older version of Unity, just pop open that shader version and make sure it's not using the clip mask function everywhere. Yep. And if you want to test UI stuff, I recommend always doing it on tablets because those will kill your fill rate, and use an iPad 3. Car shaders. Oh, I skipped the animation. That's okay. So just a quick blurb about our shaders. 90% of our shaders were all custom. We didn't use the standard shader, and mostly non-surface shaders. A few times we did. And so the breakdown is we just kept it simple. Like what we did was vertex shader, do the specular in the vertex. Then we have an ambient gradient in the vertex shader we calculate, and finally the albedo. So you'll probably hear this quite a lot, and I think you'll probably hear a lot later on if you go to optimization talks. But this is pretty much like the best way to optimize your shaders. Just put everything into your vertex shader, including post effects. If you do any kind of UV coordinate calculations, if you can do it in the vertex shader, do it there. So we have these higher tier cars. They're called second generation cars, and they're a bit shinier. You can see, ooh. So to get this shiny effect, we didn't actually use Qmax. We use the old school spherical environmental maps, or mat caps. It's an old school technique, and it's pretty fast. And I think one of the good things about it, it's easy to author. So if you don't know what WYSIWYG is, it's what you see is what you get. So you only have one texture map, and you can pretty much tell when you draw the texture map how it will look on the actual surface itself. You can see it's you can create quite different materials like gold, silver, and a plastic on the side. And it works well with normal maps and less storage than cube maps. Of course, cube maps take 6 images versus these mat caps, which is just 1. So yeah, tell your artists to try it. They might like it more than cube maps. So another thing you might have heard it before is about shader features. So you can see that's our car shader down there, and you have a lot of tick boxes there. So it's a great way to expose certain features that you can tick on and off to the artist. So sometimes they might not need per pixel specular. They should never need that, but ambient light and so on. So basically how you do this is you just add a shader feature pragma into your shader, then you add a little toggle option to your shader inspector. It's all in the Unity docs, pretty straightforward. So the thing you have to be careful with is that every time you add a shader feature, it creates lots of different permutations or variations and things. So one shader can increase the number of shaders, variations of that shader by 2 or 3 times. So you have to be kind of careful of it. So you need to make sure you check that. So how do you check that? So click your shader inspector and click that little arrow near compile and show code. In the bottom, you'll see how many variants are included. So this is for the current build platform, but you can actually select other platforms and it will show you how many variants are included. So that means for that one shader, it's made 48 different types of shaders for it, which is a lot. I think the standard shader has something in the thousands or something. So what you want to do is kind of check what is actually being included in there. So what you can do is you can hit the show button right here, and it will actually build out a list of every single variant used of your shader. So there are a lot of things that Unity actually includes that you probably don't need. Like it will include variants for certain fogs, and it also include variants for like point light cookies, spotlight cookies, and directional light cookies. So if you don't use those things, you can take them out. So use pragma skip variants. So the one below there is what we use in our game. So we actually take out a lot when we use surface shaders. I think that's actually repeated a bit, but it's pretty big, the amount. So be careful when you make a surface shader, because the standard surface shader itself, when you create a new custom one, actually makes 53 different variants. And this can add up to megabytes of data, and also Unity often compiles, I think, shaders runtime, and it could cause some lag and issues. So maybe you sometimes when you're playing a game, when a prefab instantiates, you might get that little jerk that sometimes is actually the shader loading in. and use shader feature. So there are two things, shader feature and multi-compile. The good thing about shader feature is that if there is not a material that uses that feature in your project, Unity will strip that out. So doing stuff in vertex shaders is still good. But remember that shader complexity, just don't look at the code. Always consider how much of the screen it's actually taking up. So think of it as pixels rendered times shader operations. So you can actually have something that's only renders 1 or 2 pixels, and it could be a super complex shader, but it won't really affect your frame rate. So just really take that into mind, yeah. So now we're going to talk a bit about shader profiling in Xcode. So I was thinking about doing a live version of this, but you would probably have to wait 5 minutes for it to, or 10 minutes for it to compile each time. So why not use a Unity profile? Well, often when you're on a Mac, when you open it up, it just says not supported. But I wouldn't blame Unity because I think it's an actual bug with the actual OS. And it doesn't reflect your actual hardware. So if you profile GPU stuff inside your game, you're profiling the GPU that's on your laptop, not the actual device itself. And it doesn't give you much detail. It's more just about what overheads are happening in the script. So if you really, really want to get down to it, you have to use the Xcode profiler. So basically what you do is open Xcode, then you run your game. And once it starts going, and you want to find a place that's like a hotspot when you're playing, you click that little camera icon on the bottom, and it's going to capture the GPU frame. So if you're profiling older devices like OpenGLES 2 and stuff like that, I think the new versions of Xcode don't let you do that, so you might have to get older version. So OpenGLES 2 is like devices like iPhone 5S, iPad 3, and things like that. So click that icon, then you get a lot of things. So I'll try to go over each of these bits and take you through profiling a shader. So on the left side is your kind of command buffer. So these are all the things, operations that are being sent to your GPU. Things like draw these vertices, set render states, clear stencil buffer. So just the commands that are being fed into your GPU. Then on your other side is some screen buffers. So this actually represents everything from the start to what you currently clicked on. And it'll show what's rendered up until that point right there. And you can debug other things like depth buffer and stencil. Then finally in the middle is what resources are used by the vertex and fragment shader for that current command. So it could be what actual position data is there, the actual vertex shader. So you can actually click in there and look at individual points, but I guess you wouldn't do that much. Then the fragment shader, what textures are being used, the actual fragment shader, and sampler states and stuff. So kind of those points, the command buffer, screen buffer, and vertex and fragment shader resources. So what you're going to do is once you open that up, you're going to kind of go to scroll up to your top left, and you'll see something called FPS. And if you click that, it will give you a really nice view of every single shader that's being used for that current capture and how many milliseconds that it's going to be they are using right there. So you can see we have two heavy ones, hidden blit copy and the terrain shader. So we're going to kind of ignore the blit copy because what that is just a full screen copy of your screen buffer. We use this to record like GIFs in the game, like replay stuff. So there's not much you can do to actually optimize this because any kind of full screen copy, especially on Android 2, is going to be expensive. So kind of consider if you have a GIF recording feature in your game, it could actually be dropping the frame rate quite a bit. So what we did in Crash of Cars finally, we just added a toggle so it can actually toggle on and off. So we'll just kind of look at the terrain shader right here. So we can see it's using 26.5% of the GPU resources right here. So what we can do is we can click it open, and we can actually see the commands that are being used by that shader. And then we can see if we go to the bottom, command number 211 is using 23.3%. So it's using more of that shader than these other commands right here. So what we're going to do is just kind of investigate, right? And what we can do is go back to that list right there and find 211. So we kind of want to see what happens also between 210 and 211. It's a good way to kind of visually debug and see what's happening between those two commands and what's actually being drawn. So we can actually go back to that screen buffer there. We're just going to toggle between 210 and 211. So you see what it's actually doing. Oh yeah, I know it's upside down too. And what we're doing actually is drawing that entire terrain piece. So remember I mentioned before, it's not only shader complexity, but how much it covers of your screen. So just keep that in mind too. So now we click on 211, and okay, that's why I just explained. But so how do we kind of analyze this, right? Let's go back to that resources section again, and we're going to look at the fragment shader. So inside your resources, under fragment resources, there's always something called XLATMTL main. That's going to be your fragment shader. And if you double click that, that will open up the actual code. So this isn't a code you wrote inside of Unity. This is what Unity translated into, I think this is Metal right now. But you can still kind of debug it because all shader code is a bit, I mean, it's not all the same, but you can, if you know CG shaders and surface shaders, you can kind of decipher what it's showing right there. So a handy thing it does, you can see in the red box that it gives you percentages. So it actually profiles each of those lines of code. So we see a hotspot right here. That's using 13.13%. So what I usually do when I debug shaders is I just take the line out or I set it to a constant. So let's take that line and we'll take it out and set it to 1. So what the cool thing about Xcode is, once we modify the shader, we can actually reload it by hitting that button right there. So what it's going to do is take that modified code and reprofile that frame. So we just go back and click on the FPS icon again. Then you'll have two different bars. So you have your baseline, which is what it was previously, and your modified results right there. So you can see by taking that line out, we've gone from 1.96 milliseconds to 1.55 milliseconds. The great thing about this is you can keep iterating over and over. So if you want to change something else, you go back to that command and you click on the shader and modify another line and stuff. So this is great because you don't have to go back into Unity, modify the shader, wait for 5 minutes or 10 minutes, then run the game again and profile. Keep doing this over and over and over, and I think it will save you a lot of time. And it gets you very close to the hardware. Yeah. Profile real hard, faster iteration, and you look hardcore doing it. But you also have to realize that you kind of think that Xcode is not just a way to get your product into an IPA file. There's lots of tools on it, like profiling. Because I'm lazy, like I'll even go in and you can modify the IO to CPP code and actually rerun the build. So you can do quite a lot in Xcode because all it does is generate C++ code at it, and that C++ code can be modified. So that will lead you to faster iteration times, and when you're on a tight deadline and you want to recompile everything, you can modify the C++ code and build it. So it's a lifesaver sometimes. So explore Xcode and explore the instrument tools on it. So would you rather do questions or experiments? Who wants to do questions? Anyone have questions that more? Okay, I'll just go over experiments and do QA after. So I talked to you a bit about case shadows. I'll talk to you how we can do kind of real-time soft shadows. So case shadow map is pretty simple. So all a light does basically is generate a depth buffer from the viewport of the light. Then we use that to render shadows onto objects. So a simple optimization is just don't render that depth map over and over. Save it to a texture and sample it. Then you don't have to re-render any static stuff. So one thing with shadow maps on mobile devices, I think Metal has some features for this, but it's hard to do real-time soft shadows. So real-time soft shadows can be things like PCF and PCSS. So PCF, percentage close filter, is basically a way to simulate soft shadows by sampling a bunch of shadows around a specific point, then averaging them. Similarly is PCSS, but it actually gives more of a better penumbra, which is that kind of soft outline on your shadows depending on the distance from the object. So a basic PCF shadow requires you to sample a shadow map 9 times, which is quite a lot, and it's way too slow for mobile devices. So that's the issue, is that shadow maps are not really color data, the actual depth data. You can't blur depth. If you have 2 points that are completely different and you try to blur those 2 points together, what's going to happen is that you're going to get a point in the middle, which makes no sense. So there's one solution to it called variance shadow maps. So this is a pretty old technique. And so what we actually do is we store 2 of those kind of shadow maps. One is the depth and the depth squared. So we can take those 2 shadow maps, we can actually blur them before we sample them. So I said you're not supposed to blur shadow maps, but you can in this case, because it uses something called, I don't know how to pronounce this, but Chebyshev's inequality. So you can look a bit more into that link above there. But what this basically does is it lets you pre-blur a shadow map. So the big plus of this is using a shadow map to do PCF. You have to sample it 9 times after you render the shadow. So you're doing that pixel operation on a high resolution screen. But in the case of variance shadow maps, you can blur depth maps before in a lower resolution, then sample them on your objects. So we did a bit of test on Crash of Cars. You can see that's different blur ratios. Then we have soft shadows right here. Should move more. Yeah. So it actually looks like the baked shadows we baked in, but running at real time. So I kind of profiled this, and it runs actually on devices like iPad 2 and stuff. So look at variance shadow maps. It could be a good option. There are some issues with it. I won't really go into detail with it, but mostly about overlapping geometry, but most of the time it works pretty well. So Unity has something called light probe proxy volumes, and they're pretty cool. So if your artists ever use light probes in the game, that's basically a way to bake lighting data into a volume using spherical harmonics. And what this basically means is any dynamic object can receive kind of that scene lighting that you baked into your light map. So Unity released something called Light Probe Proxy Volume, which is a souped up version of that. Because if you put down light probes, usually you'll put down whatever, like for each point around the scene, you'll put down 20, 30, or I don't know how many. But light probe proxy volumes are a lot more dense. It could be in like the thousands and stuff. So all dynamic objects can receive lighting. And it was used in big budget games. It's actually conceived when they're making this game called Recore to do dynamic lighting, but shader model 4. So that's a big downside. Often I'll see a new feature in Unity, but it'll be aimed at something not mobile. Everything has to be like something shader model 3 or 4, things like instancing and stuff. So we can actually get around of this by kind of making our own proxy volume. So I think the main issue is no 3D texture support and sometimes dodgy floating point textures. So what we can do is, to get over the 3D texture, we can actually map 3D textures to 2D textures pretty simply, because it's just taking those and placing them into a grid. So the other issue we need to do is, how do we interpolate between 3D textures? Because 3D textures can interpolate between X and Y coordinates and Z coordinates. So we just do a simple trilinear filtering. So what we do is take 2 samples, or 2 of those little grid pieces, and if we want to blend between them, we can just do a filter between the 2. So that solves the 3D texture issue. So I know I skipped over a whole bunch of stuff, but basically when we can wrap a 3D texture into a 2D texture, that solves that issue. So now we have a way to bake that spherical harmonic lighting data into our texture. Then it'll become a volume that we can place over our scene. And you can see this is a result of one of my experiments at home. You can see particles can receive and cast shadows, and all that lighting is baked in there. So it's a pretty good way to think of using textures creatively. And I've done other experiments too with 3D textures mapping to 2D textures. You can get things like, if you played the game Fortnite, they use something in there called sign distance fields to calculate shadows. It basically gives you the cheap way to raycast into the scene and compute soft shadows. That's actually possible on older devices like this using the same trick, just wrapping a 3D texture into a 2D space. Of course, it's going to use a lot of memory, but any kind of volumetric texture takes heaps of space. So it ran on Nexus 7, 2012, that kind of stuff. So it's pretty good. And the overhead, basically the overhead for calculating lighting using spherical harmonics is just pretty much a dot product for each color channel. Yeah, so work closely with your team. Give them what they need, but don't give them everything. That makes them creative. And don't black box things. Make a lot of tools. And you'll be kind of surprised what artists can do when you give in certain shaders and stuff. They do some pretty creative stuff. Yeah. Was that everything? Wow. So that was 100 slides in. Thanks for listening. I know I blasted through everything, so yeah, come up to me and talk to me if you have any other questions. I like talking about graphics and stuff. These were just a bit of like a bag of tricks you can use while you're making your game. So anyone have any questions? Yep.
One quick one. What was the name of that shadow technique they used in Fortnite?
Sign distance field shadows. Yes. Yes. Any other questions?
We share slides?
Yes. I think I'll upload them somewhere. I'm not sure where I'm supposed to yet, but yeah. Sorry?
Post them on your Twitter?
Oh, yeah. I'll post them on Twitter stuff, yeah. Good idea. Yeah. Anything else? Okay. Thank you for coming to my presentation. I hope I didn't ramble too much. Yeah.